Hey guys, it's time again for some more physics. Today we're going to talk about Newton's first and third laws. Newton's first law is also known as the law of inertia. Okay, now cut through this one. I'm going to ask you occasionally a couple of questions. When I do, hit pause, think about your answer, maybe write it down on the left-hand side of your notebook, and we'll come back to them, or we'll answer them in just a second. So here's our first one: true or false? Even if no force acting on a moving object, it will eventually stop. True or false? Okay, let's keep going, just one more. All right, a moving object must have a force acting on it to keep it moving. True or false? Okay. We're going to go through this set of notes, and at the very end, I'm going to come back to these questions, and we're going to go over those. All right, so stuck with inertia. So let's go back to Isaac Newton, which was 17th, 18th century. And this is his first law of motion. An object at rest will stay at rest. Excuse me. An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by a net external force. Things I want you to pay attention to: at rest, remains at rest, object in motion, constant velocity. But here's the important one that may not have been something that you learned around the first time: net external force. So it's not just that they're going to keep doing what they're doing. So they're going to keep doing what they're doing until something else makes them stop. The old childhood taunt: make me. All right? So inertia is defined as an object's resistance to a change in motion, and mass is a measure of inertia, and units are kilograms. So anytime you're talking about mass or you're talking about inertia, and I have seen questions like this, guys: which has the biggest inertia? Whatever has the biggest mass. All right, so kind of big star on this one. Make sure we know that we measure inertia with mass, and that means if it has kilograms, it's inertia. And so basically, the more mass an object has, the more inertia. The easier it is to change, the harder it is to change its motion. The less mass, the easier it is to change its inertia. All right, so here's an example of an object at rest stays at rest until acted upon by a net force. Do you ever try and pull a book out from underneath a bunch of other ones? Boom, if you do it right, you're going to go ahead and poosh, they're not going to do anything. Or you ever see the trick where a waiter pulls the tablecloth out from underneath of everything? Inertia. That same one you saw in the mass and weight one, also an inertia. Okay? Here's examples, and here's our other one. An object at rest stays at rest until acted upon by a net force. Lady over here, can't tell me she's not putting a force on that big old rock, but it's still not moving. All right, so here we go. Ooh. This is a lesson in why we use our seatbelts. The car stops. All right, so you and the car are both going, however fast you're going, your car stops. If you don't have a seatbelt, you're going to keep going. All right, keep that one in mind. That also shows up sometimes in quizzes and tests because it's a safety issue. So basically when it comes to automobile safety, that works as well. Here's another one. You may not realize this, but inside of our bodies, the things inside of our bodies, like our organs, aren't really like firmly attached. So any of you have ever gotten a concussion, or you hear about concussion injuries? Concussion is inertia in action. Your physical body stops. All right, your skeleton stops moving, but your brain's not fully attached to your skeleton. So what happens? Your brain bounces around. You stop, your brain keeps going until it hits your skull. All right, and that's a concussion. Don't want those. Okay. Also, an object in motion stays in motion until acted upon by a net force. Now, here we go. That's just another demonstration of it. Okay. Inertia in action. What is our inertia? Our inertia is this guy right here. Right. Inertia is not the crash. Inertia is what keeps the guy moving forward. All right. So I want you to think about this one. And when you pause, when you think of the question. Imagine a place in space far from all gravitational frictional influences. You visit that place and you throw a rock. What's going to happen to that rock? Hit pause. All right. Did you choose B? Okay. That rock is going to continue in motion in the same direction at constant speed because there's nothing there to change its motion. There's no air friction. There's no gravity. There's nothing. It's just going to keep going. Next question. An object is moving through outer space in a straight line and with a constant speed of 4 meters per second. How much force do we need to keep that object moving at that speed and in that direction? Okay. Some, lots, or nothing. Did you choose nothing? I hope so, because if it's moving at a constant speed, it is an object in motion. So it's just going to keep on doing what it's doing. All right, let's take a look at this one real quick. Let me see. I need to grab a quick snapshot of this. Got a lot of stuff in here. Okay, so we're twirling our yo-yo in outer space. The ring snaps. What happens to that yo-yo? Okay, let's take a look at this. All right, so here we are. And here we go. So what's happening? Okay. Watch my amazing art. All right, so here's our string going out. Here's the yo-yo. What's going out? It's going around and around and around. And it breaks right here. What's going to happen to that yo-yo? Where's it going to go? Is it going to go this way? Is it going to go this way? Is it going to go straight down? All right, what do you think? It's going to go straight. All right, so if you take it in terms of like a tangent line, find another one. If this is our circle, the tangent path, that straight path at that point, that's the way it's going to go. So it always goes off straight. Okay. What else we got in here? Well, it takes forever to load. Okay, here's our fourth question. Mac and Tosh are arguing in the cafeteria. Mac says that if he flings the jello with a greater speed, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with and why? Are you talking to a friend? Hit pause. Think about it. Okay, welcome back. All right, who is right? Tosh is right, because it doesn't matter how fast you're going, all right, your inertia is based off of your mass. Let me see. Now, Fred spends most of his Sunday afternoons at rest on the sofa, watching pro football games and consuming large quantities of food. What effect, if any, does this practice have on his inertia? What do you think? Well, if you don't exercise and you eat lots of food, what happens? You gain mass. So if you gain mass, you're gaining inertia. All right. Now, let's do a little bit of work with this as well. Terminal velocity. We've talked about this before, so we know what terminal velocity is. It's the final speed that a falling object reaches before the air resistance and the weight of the object are equal. So this part right here, whoops. This part right here, that is terminal velocity. Okay, so I'm going to go back to that other page really quick. So mathematically, when we're talking about Newton's first law, so we talked about conceptually. Let's talk about it mathematically really quick. Mathematically, Newton's first law is about all the forces acting on one object. Okay, and with all the forces that are acting on that object, and if all the forces, net force, is equal to 0, then we say it's balanced, it's in equilibrium. Things are moving, it's at rest, or constant velocity. Okay, some of those concepts we dealt with in the last one. Okay, so that if I'm pushing on something with 3 newtons of force and friction is 3 newtons of force, all right, the law of inertia tells us that it's balanced and it's going to stay at rest. Or if it was moving, it was going to stay moving. So we got to keep that in mind about Newton's first law. Newton's first law lets us mathematically tell if things are balanced or unbalanced. Next up, just kind of summarize the entire thing after it takes a second to load. All right, here's our summary. That mass is a measure of inertia. Mass resists change in motion. And unbalanced forces is what causes that change in motion. So if it's balanced, you're going to keep moving what you're doing, okay? And if it's unbalanced, your motion is going to change. So Newton's first law is a way to say if things are balanced or unbalanced. Let me see. Take that summary sheet and add a little bit more to it. Okay. Let's take a look at this. Whoops, wrong bit. Here's what we do. So if we go, if the net force is equal to 0, balanced. Net force is not 0, unbalanced. All right, motion changes. And if motion changes, there's an acceleration. Can't spell. And if it's balanced, motion stays the same. Now let's talk about, let's go back to those first true-false questions that we were dealing with last time. Okay, so I'm going to go all the way back up. I'm really hoping that's stuck in there the way I wanted it to. Where's our first batch? Our true or false questions. Okay, true or false? Even if no force acts on a moving object, it will eventually stop. That should have been false. Newton's first law says that objects in motion will keep on moving. So that is a false statement. It will only stop if there's a net external force. And a moving object must have a force acting on it to keep moving. Also false. You don't have to have a force to keep it moving. Think about with your free body diagrams the other day, the thing with the puck sliding across the ice, no friction.